Dear students, today I am going to talk about continuity. So let's start with the definition of continuity. So here is the definition. So let D be any non-empty subset of R, and so let F from D to R be a function, and we take a point, say A belongs to D. Okay, now then we say if the function f is continuous at the point A if for any sequence, or you can better to say that any convergent sequence xn in the domain D which converges to the point A, we have f of xn converges to f of A as n tending to infinity. That's mean to define the continuity of a function at a point, say A, we have to take the point from the domain. So this is the first observation, and another observation is that you can choose any sequence, that is any convergent sequence converges to A. So you don't need to take xn not equal to A. That's mean some of the term of xn can be A as well. We do not have any such restriction. Now we note that so first observation is if A belongs to D, that is if A is in the domain but A is not a limit point, of the set D, then F is always continuous at A. Why? Because if A is not a limit point of the set D, then the only sequence which converts to A is the constant sequence only, right? You have seen this in your sequence. That's mean if you take any sequence xn which converts to A, then that sequence should be a constant sequence, or you can say eventually constant sequence. That's mean after some stage all the point, that is all the xn should be equal to A. That's mean f of xn is same as f of A after some stage, so it is obviously converts to f of A. So there is nothing to prove. So by definition then f is continuous at A. Now another observation is if A belongs to D and A is a limit point of the set D, then F is continuous at the point A if and only if limit x tending to a f of x, that is the limit of the function f at x equal to a, should be equal to f of a. Now this is also clear from the definition. Why? Now suppose if you take a sequence xn which converts to a, but xn is not equal to a, then f of xn converts to f of a, because f is continuous at the point a, right? So therefore the limit of the function f at x equal to a is f of a, and it is true for the conversely as well. Now suppose if for any sequence xn in D such that xn is not equal to a and xn converts to a implies f of xn converts to f of a, then if you choose a sequence xn where some of the term are a as well, then also f of xn will be converts to f of a, right? So this is if and only if condition. Now what do you mean by f is not continuous at the point a? Now here I note you can use it as a definition as well. So another observation. So if there exists a sequence xn in D such that xn converges to a, but f of xn does not converges to f of a as n tending to infinity, then we say f is not continuous at a, right? You can see this from the definition of continuity as well. This is just a negation of the statement that f is continuous at x equal to a. Fine. Now there is another term called continuous on a set. Now here I can write as a definition. So let f be a function from D to R where D be a any non-empty subset in R, okay? Now if f is continuous at each point of D, then we say f is continuous on the set D, okay? So it may happen that f is not continuous on the set D, but f is continuous at some of the elements of D. So when we say that f is continuous on the domain D, that means f should be continuous at each of the point of D. So if f is continuous at almost every point but except 1 or 2, then also we will say that f is not continuous on the domain D, okay? Now here we see some examples to understand the definition. So here is the example 1. So now let f be a function from r minus 0 to r defined by say just f of x equal to 1 by x, okay? Now what can we say about the continuity of the function f? Now here first choose, so let a be an arbitrary element from the domain r minus 0, right? And let xn be a sequence, you can say convergent sequence as well, sequence in the domain r minus 0 such that xn converges to a. Okay, now since a is not equal to 0, so by the algebra of the sequence we know that f of xn, right, is, sorry, we can say here this 1 by xn converges to 1 by a, because xn and a all are not equal to 0. This is for all n, and this is by the algebra of sequence, right? Now what is my 1 by xn and 1 by a? So that is f of xn and f of a, right? So that implies f of xn converges to f of a as n tending to infinity, right? Now since xn is a arbitrary sequence, therefore we can say that f is continuous at a. Now since the sequence xn is arbitrary, therefore f is continuous at the point a, right? Now again, since a is arbitrary, that means f is continuous at every point in the domain, right? Therefore we can say that f is continuous on the domain r minus 0. Fine. Now here is the another example. Say example 2. Now let your f is a function from r to r be a function defined by, say, f of x equal to, say, 1 if x less than 0, say equal to or equal to minus 1 or equal to 1 if x is bigger or equal to 0. Now discuss the continuity of the function f. So here is the solution. So we choose 3 types of points. So first of all we can assume that, say, case 1, so let a belongs to r be such that a less than 0. Okay, so that implies a belongs to the interval minus infinity to 0. Fine. Now let xn be any sequence in the domain R such that xn converges to a. Right? Now since xn converges to a and a belongs to the open interval minus infinity comma 0, therefore there exists a natural number n such that xn belongs to that interval for all n bigger or equal to n, right? That's mean after some stage all of the term will be in that interval. Fine. Now that imply f of xn equal to minus 1 for all n bigger or equal to n. Right? Now that imply f of xn converges to -1, and see, since a is negative, so f of a is also -1, right? So that is f of a as n tending to infinity. Therefore, we have chosen an arbitrary sequence xn converges to a, and we get f of xn converges to f of a. Thus, f is continuous at x equal to a. Right? Now, similarly, we can prove that if we choose a bigger than 0, right? Then similarly, we can prove that f is continuous at x equal to a. So we can write here also. So let xn be a sequence converges to a which is belongs to 0, infinity, right? Therefore, after some stage, all of the xn will be in that interval. That means there exists a natural number n such that xn belongs to that interval 0 infinity for all n bigger equal to n. And again, by the definition, f of xn will be 1 for all n bigger equal to n. Therefore, f of xn converges to 1, and which is just my f of a as n tending to infinity. Now, since xn is a arbitrary sequence, therefore f is continuous at a. That's when if we choose any negative point and if we choose any positive point, then we can show that f is continuous at those points, right? Now the only case left is take a equal to 0. Fine. Now we show that this is not continuous. That is, f is not continuous at x equal to 0. Why? So, if we take a equal to 0, then what is my f of 0? See, the question, then f of 0 is 1. Right? Now we can choose xn equal to -1 by n. Then f of xn equal to -1 and xn converges to 0, right? So here xn converges to 0, but f of xn converges to -1, which is not equal to 1, which is my f of 0, right? So we can write here so thus there exists a sequence xn in our domain R such that xn converges to a, but f of xn does not converges to f of a. So therefore f is not continuous at x a equal to 0. So better to write here 0. Fine. Okay. Now we refine this problem a little bit. Now here is the example. So what was that example? That is example 2. Say now example 3. Now let f again R to R be a function such that f of x equal to 1 when x belongs to rational and equal to -1 if x belongs to irrational, say R minus q. Okay, now again discuss the continuity of the function f. Now we choose two types of points to solve the problem. So here is the case 1. So let a be a point which is rational. Then f of a will be 1. Now let xn equal to say a plus root 2 by n. Then obviously xn, each of xn is irrational, right? Then xn belongs to R minus q and xn converges to a. Now since xn converges to R minus q, therefore f of xn will be -1, right, for all n. So therefore f of xn converges to -1 and which is not equal to 1, which is my f of a. So we have a sequence xn in our domain R where xn converges to a but f of xn does not converge to f of a. So thus we can write xn converges to a but f of xn does not converge to f of a. So therefore by the definition f is not continuous at the point a. That means x is not continuous at the rational points. Now what about the irrational points? This is the case 2. So let a belongs to R minus q, right? Now we know that each irrational has a decimal representation, right? Now first of all here, then f of a will be -1, right? Now so let a equal to some plus minus a0 point, say a1, a2, a3, a4, a5 ... So this is the decimal representation where a0 is either 0 or natural number. Therefore we can write a0 belongs to the set n union 0 and the other ai must belong to 0, 1 up to 9, right, for all I. Okay, now we assume Rn equal to that plus minus a0 point a1, a2 and we stop at an. That means each of Rn is a rational number. Now then Rn belongs to q and Rn converges to a. Fine. Now since Rn belongs to q, therefore f of Rn by our definition that is 1 for all n, right? So this is converts to 1 as n tending to infinity, right? But what is my f of a? F of a is -1. Therefore this is not equal to f of a. So that's mean Rn converges to a but f of Rn does not converge to f of a. So we can say that f is not continuous at a. So we have seen that if a is rational, then also f is not continuous at a. Even if a is irrational, then also f is not continuous at the point a. Therefore f is nowhere continuous on the domain. So we can write that therefore f is nowhere continuous on the domain. Okay. Now again I wish to refine this problem a little bit, and here is the next example. So example 4. Let f be a function again R to R and defined by f of x equal to 1 when x belongs to rational and equal to say x when x belongs to irrational, R minus q. Now again discuss the continuity of the function f. So here is the solution. Now again we split this problem into 3 parts. So first of all we assume a not equal to 1, but it is a rational point. Okay. Now then what will be my f of a? Now f of a will be 1, right? Now again let xn equal to a plus root 2 by n, which is irrational. Then xn belongs to r minus q and xn converges to a. But f of xn, since xn are irrational, therefore f of xn will be the same one, and this is converts to a, which is not equal to 1 f of a, right, by our assumption. So thus you have a sequence xn which converts to a, but f of xn does not converts to f of a. So therefore f is not continuous at a. Now take the case 2, that is the similar as the previous problem. So let x belongs to, say a belongs to r minus q. Then f of a will be a, right? Now say let a equal to again say plus minus a0 point a1 a2 a3 a4. So this is the decimal representation of a, where a0 belongs to natural number union 0 and ai belongs to the set 0 1 up to 9. Fine. Now again we take Rn equal to again plus minus a0 a1 a2 up to an. Now then Rn belongs to rational and Rn converges to a. Now this implies f of Rn, which is 1, that is converges to 1, and obviously that is not equal to a, which is my f of a. So therefore f is not continuous at a, that is at all the irrational points. Now the only case is let a equal to 1. That's mean we want to discuss the continuity of the function at x equal to 1. Now let xn be a arbitrary sequence such that xn converges to 1, right? And we wish to prove that f of xn is also converges to 1. Now we prove this by our definition of a convergent sequence. So first of all, choose arbitrary epsilon bigger than 0. Okay? Now since xn converges to 1 as n tending to infinity, therefore there exists a natural number n such that mod of xn minus 1, that is less than epsilon, for all n bigger equal to the number n. Okay? Now choose a number m bigger equal to n, that n. Okay? Now if xm, that is the mth term of the sequence xn, is rational, then f of xm will be 1, right? Then mod of f of xm minus 1, that will be 0. This is less than epsilon, right? Now if xm is irrational, then f of xm will be same as xm, right? Then mod of f of xm minus 1, that is equal to xm minus 1, this is less than epsilon, right? So therefore mod of f of xm, we can write xn minus 1, that is less than epsilon, for all n bigger equal to n, that is f of xn converges to 1, which is my f of 1. Okay? Since the sequence xn is arbitrary, therefore we can write that f is continuous at 1. So therefore f is continuous only at x equal to 1. Okay? Now I shall give another example. Now that is little bit tricky. So let f open interval 0 1 to r be a function defined by, say, f of x equal to 0 if x is irrational, say 0 1 minus the set q, okay, and equal to 1 by q if x equal to rational in the domain 0 1, that is of the form p by q belongs to 0 1, so intersection q, where p and q are relatively prime. Now again we ask the same question, discuss the continuity of the function f. So here we divide this problem into two parts. So first we prove that f is not continuous on rational points, and then we prove that f is continuous at each of the irrational points. So first of all, case 1. So let R, which is my p by q, is of the form this, belongs to 0 1 intersection q. Okay, then what is my f of r? Now f of r will be, by our definition, 1 by q, and this is not equal to 0. Now let xn equal to r plus, say, root 2 by n. Okay, now obviously these are the irrational number, so r minus q, but it may not happen that all of this number belongs to the open interval 0, 1, right? But we know that xn converges to r, and this r belongs to open interval 0, 1, right? Therefore, there exists a natural number n such that xn belongs to this open interval 0, 1, and obviously these are the irrational number. We can write this is minus q for all n bigger equal to n, and then f of xn, that is 0 for all n bigger equal to n, by our construction, right? So thus this is a eventually 0 sequence, so f of xn converts to 0, which is not equal to f of r. So we have a sequence xn which converts to r, but f of xn does not convert to f of r. So therefore f is not continuous at x equal to r, where r belongs to that open interval 0, 1 intersection q. Fine. Now we prove that f is continuous at all the irrational point between 0 and 1. Case 2. So let a belongs to open interval 0, 1 minus q. That is, a is a irrational number between 0 and 1. Now then, what is my f of a? That is 0 by our definition, right? Now let xn be any arbitrary sequence in the domain 0, 1 such that xn converges to a, right? And we wish to prove that f of xn converges to f of a. So for that we prove this via definition of the sequence. So let us choose any arbitrary epsilon bigger than 0. Now we claim that so there exists n belongs to natural number such that mod of f of x minus f of a, which is, since f of a is 0, so that is mod of f of x only, less than epsilon for all n bigger equal to that n. and that will imply that f of xn converts to, or you can write here xn, that will imply that f of xn converts to f of a. Okay. Now first we need one observation. You can check that the number, you can say the number of natural numbers, say n, such that n is less than equal to 1 by epsilon is finite. Right? This is simple because it is a, so we have a upper bound 1 by epsilon, so we have at most finite number of natural number, right? And this is 1 to up to that box of 1 by epsilon. Fine. Now this will imply that is that equivalently we can say that the total number of natural numbers in such that 1 by n greater equal to epsilon is finite, right? Now again this will imply, so you can write thus the number of rational number m by n where 1 less than equal to m strictly less than n such that 1 by n greater equal to epsilon, this type of rational numbers is also finite. Right? That is the collection of rational numbers m by n where 1 by n bigger equal to epsilon is finite. Why this collection is finite? Because for each 1 by n we have only limited number of rational numbers, say 1 by n, 2 by n, 3 by n up to n minus 1 by n, right? Okay. Now this is equivalent to, we have only finite number of rational numbers say m by n in the open interval 0, 1 such that 1 by n greater equal to epsilon. In other words, f of m by n, that is 1 by n, and this is greater equal to epsilon, right? Now we assume, so let these numbers are, or you can say these rational numbers are, say R1, R2, R3 up to Rk. Okay, so this R1, R2, R3 up to Rk are the only rational numbers such that f of Ri greater equal to epsilon. Okay. Now what we will do, so this is the case, so here, so suppose this is my A, now suppose this is my R1, say this is my R2, say this is R3, say this is R4, say this is R5, so these are the finite numbers, right? So finite number of rational numbers. Now what we will do, we just calculate the distance between A and Ri, okay, and we take the minimum distance. Suppose in this case, this is the minimum distance, we call it, that is delta. So we have an interval containing A. So now let delta equal to minimum over 1 less than equal to I less than equal to K, and the minimum is distance between A minus Ri. Therefore, we have an interval, say A minus delta comma A plus delta, such that all of this Ri does not belong to this set, right, for all I. So we can write that Ri does not belong to A minus delta comma A plus delta for all I equal to 1 to K. Fine. So that's mean so if we have a rational number R, which is sum of the form m by n, belongs to A minus delta comma A plus delta, then f of R, that is 1 by n, right, and that is strictly less than epsilon. Therefore, so if some number C belongs to A minus delta comma A plus delta, then what can we say about f of C? Then if C is rational, say C equal to m by n, then f of C equal to 1 by n, that is less than epsilon, and if C is irrational, then f of C equal to 0, and again this is less than epsilon. Fine. Now we are almost done. Now since we have xn converges to A, so therefore there exists a natural number n such that xn belongs to A minus delta comma A plus delta for all n bigger equal to n, right? And we have already proved that if we have some number xn belongs to A minus delta comma A plus delta, then f of xn should be less than epsilon. Now that implies f of xn, which is positive, strictly less than epsilon. So thus mod of f of xn minus f of A, this is just f of xn, this is less than epsilon for all n bigger equal to n. Now since epsilon is arbitrary, therefore f of xn converges to f of A as n tending to infinity, right? Now again, since the sequence xn is arbitrary, so you can say f is continuous at x equal to A, where A belongs to open interval 0 1 minus q. That is, f is continuous at all the irrational points and f is discontinuous at all the rational points. Fine. Now these are all about the problems. Now I wish to prove few properties for continuous function. So here is the first property. So let f closed interval ab to R be a continuous function continuous function means f is continuous at every point on the interval a b. Okay, now then we prove that if f of a, that is that the left boundary point, that is f of a bigger than 0, then there exists a positive delta bigger than 0 such that f of x bigger than 0 for all x belongs to the interval a comma a plus delta. Okay, similarly we can write now if f of b bigger than 0, that is the value of the function at the right end point, the right boundary point, then there exists a again positive delta such that f of x is bigger than 0 for all x belongs to that b minus delta comma b, and if say f of c bigger than 0 for some c belongs to the open interval ab, then there exists a positive delta such that f of x is strictly bigger than 0 for all x belongs to c minus delta comma c plus delta. Actually the proof of this property is same as which I did for the limit. Anyway, I can solve here as well, but I shall solve only the property 3. Okay, and the property 1 and 2 is similar to the 3 only. So here proof of 3. So first of all, since c belongs to the open interval ab, right, therefore there exists a natural number n such that c minus 1 by n comma c plus 1 by n, that open interval will be subset of a comma b for all n bigger equal to capital N. You can prove this via Archimedean property. This is the simple one. Now we claim that there exists m which will be bigger equal to capital N such that f of x will be bigger than 0 for all x belongs to that c minus 1 by m comma c plus 1 by m. Okay. Why? Because if there is no such m, then for each natural number n bigger equal to capital N, we must have a number, say xn, belongs to the interval c minus 1 by n comma c plus 1 by n such that f of xn is less than equal to 0, right? Now obviously since xn belongs to c minus 1 by n comma c plus 1 by n for all n bigger equal to n, therefore xn converges to c as n tending to infinity. Now since f is continuous at c, therefore f of xn should be converges to f of c as n tending to infinity, right? Now what is my f of xn? That is f of xn is less than equal to 0, right? Therefore f of c, which is limit of f of xn, right? Now each of the f of xn is less than or equal to 0, so their limit will be less than or equal to 0, and this is a contradiction. Right? Because it was given that f of c is strictly bigger than 0. So therefore we must have a natural number m such that f of x will be bigger than 0 for all x belongs to c minus 1 by m, comma c plus 1 by m. That is, we can assume that delta equal to 1 by m. Fine. Now similarly, if we assume that f of c is less than 0 for some c, then also we can find one interval containing c such that f of x is less than 0 throughout the interval. Okay, that's mean, in other words, you can say that if f of c is not equal to 0, then we will have an interval containing c such that fx will be not equal to 0 on that interval. So this is the important property of continuity. Fine. Now I just want to state another definition for continuity. This is sometimes called that epsilon delta definition, or informally you can say that epsilon delta definition. But since I gave the sequential definition, so I write this definition as a theorem. Okay, so let f d to r be a function where d is a non-empty subset of r, right? And say a be a point in D. Now then f is continuous at the point A if and only if for any epsilon bigger than 0 there exists a positive number delta such that whenever x minus a less than delta and x belongs to D, then we will have mod of f of x minus f of a less than epsilon. Okay. So if you want to prove that a function is continuous at a point A, then you can use this property as a definition as well. So sometimes we call this a epsilon delta definition. But I am not going to prove this one because this is the similar one as I proved in the limit case. There also I gave one sequential definition and another epsilon delta definition, right? And I proved that both are equivalent. Now similarly, you can prove that this property is equivalent to that sequential definition. Okay? So I stop here today. See you in the next lecture with more properties of continuity.